to start off talking about how automobiles work, and they're an example of a heat engine, which is why they sort of fit into this part of the story. I told you last time that a conventional automobile, actually I roll back and show you those pictures. Conventional automobile uses cylinders that go through four strokes. So the full cycle of its operation consists of 4 strokes. There are engines that involve only 2 strokes that effectively combine pairs of strokes. Like lawnmowers have those, but for cars it's these 4-stroke engines. The first stroke, starting somewhere in the cycle, the obvious place to start is the induction stroke, where you bring fuel and air mixture into the cylinder as the piston moves out. The compression stroke seals the cylinder and then squeezes that fuel and air mixture to high pressure and density and temperature. The power stroke actually begins with igniting the fuel and air mixture with a spark, and then it extracts mechanical work from that hot burn gas by letting it push hard on the piston and shove the piston as the piston moves out. So that's where that's the origin of the automobile's power. And finally, the last stroke is the exhaust stroke, where it just squeezes the burned gas, what's left, out of an exhaust valve. Incidentally, important things are 3 of those strokes consume work. That is, the engine has to do work on the gas. Only one of them has the gas do work on the engine, the power stroke. The others are cost energy from the engine, and that is one of the reasons why engines have typically 4 or more cylinders, timed so that one of them is always going through the power stroke, and therefore providing the power that the other cylinders need temporarily to get the job, some task done. Another observation, and an important one that has to do with heat and thermodynamics, is that when you open the valve at the end, at the beginning of the exhaust strokes, having let the gas, let me go back to the power stroke. During the power stroke, the gas does work on the piston. It shoves the piston out. Are there any consequences for the gas? Well, yeah, it's giving up energy. Where does that energy come from? It comes from the thermal energy of the gas. That thermal energy is becoming work, and this by itself would be the law of entropy would be upset at this, but the heat is actually flowing from hot to cold. It is not reducing the entropy of the world. There are other things going on that compensate for that fact that thermal energy is becoming mechanical work. The gas is spreading out, occupying more space. At the end of the power stroke, you might think, well, has the gas used all of its thermal energy to do work on the piston? The answer is no. Well, first of all, it's not going to go below room temperature. Well, I shouldn't say that. You wouldn't expect it to go below room temperature, but in fact, it doesn't even go to room temperature. It's still hot by the time it gets to the end of the stroke. This is part of in effect, the law of entropy protecting itself, enforcing things. You can't get all of the thermal energy out of the hot burn gas and turn it into work, 100% of it. Can't do it. The gas, by the time the piston reaches its original location, where it was before the compression stroke, the gas is still hotter than it ever was, than it was before the compression stroke. So these 2 strokes are symmetric. There's the compression stroke, there's the power stroke. Compression stroke, the piston's going in. The power stroke, the piston's coming out. And you might think that it sort of goes back to where it started from. Everything's all settled. Well, no. The act of burning the gas, spiking the temperature way up, shifts the whole temperature profile for the power stroke to a higher level. So that, although I'll go flip back and forth and maybe drive you crazy. During the compression stroke, remember, as the gas is being squeezed, its temperature is going up because work is being done on it. I showed you that things can burst into flames in the presence of this gas. It's been air that's been heated to that temperature. I'll talk more about that in a minute. But so the act of compressing the air increases its temperature. The act of uncompressing it, letting it do work on you, cools it. Does it cool it all the way to room temperature? No, not in this situation, because once you burn the fuel and air, the whole temperature profile of the power stroke is higher. It's much hotter at the beginning of the power stroke, and it's still hotter at the end of the power stroke. Is that followable, or questions about what I just said? The temperature goes up on the compression stroke, woof, sudden jump in temperature, and the temperature goes down on the power stroke, but not all the way back down to where it started. What are the consequences of this? The consequences of this are when you start the next stroke, which is the exhaust stroke, what you're going to squirt out is hot gas. It's not at room temperature, it's hot. This is part of the waste heat that inevitably comes out of an engine. You can't make it 100% efficient, turning heat into thermal energy into work. The other thing is the pressure of that gas doesn't go back down to atmospheric pressure. It's still high also. So everything, the power stroke, it starts at high temperature, high pressure, high density, and it swoops down as it continues to lower temperature, lower pressure, lower density, but it's still hotter and at higher pressure than it was before the start of the compression stroke. If you follow the need for the desire for them to be symmetric, it would be wonderful if you could go up in temperature and pressure and density during the compression, bang, create all this thermal energy, and then swoop all the way back down to where you started from. Room temperature, room pressure, everything. You can't get that. That would violate the second law, the law of entropy. So the consequence that I'm leading up to is, first off, it ejects hot gas. You know this. There's a lot of heat in the exhaust system coming out the tailpipe. That's part of the waste heat. Unavoidable. The other thing is, when they open that exhaust valve, this valve up here that lets the exhaust out, there's high pressure gas still inside the cylinder. It jumps out of that opening, the valve, and makes a pop sound. So if you do not have, if the exhaust system of a car has holes in it, you will hear pop, 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 the loud roar of an engine that's not muffled properly. When the motorcycle goes by, what are you hearing? You're hearing the exhaust valve open and let high pressure gas jump out. Pulse, 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 pulse. All right? What's a muffler do? It smooths out the pulses. It spreads out those pulses in time by making them go through baffles, so that instead of being pop, 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 it's more tries to smooth it out and make it less noisy. But that's what you're hearing, is you're hearing part of the waste heat, high pressure gas being released in pulses from all the cylinders. Unavoidable. Questions about that? I'm going to try to explain the world here. Clarissa explains it all, which I guess is before your time. Okay, efficiency limits. I talked a little about these sorts of things before. The hotter the hot, and the colder the cold. When you're letting heat flow in a heat engine from hot to cold, the bigger that temperature difference, the more of the larger fraction of the heat you can divert and turn into work. So it pays, in effect, to burn the fuel and air as hot as possible. And there is some control. The more you compress the fuel and air mixture before you ignite it, the higher the temperature spikes. And the hotter the hot is. Correspondingly, the colder it is outside, in principle, the more efficient the engine becomes, because that's where the waste heat is going. So increasing the temperature difference leads to more efficient engines. There are consequences to that, though, we'll come to. And obviously, that's in theory. In reality, it's hard to achieve perfection. So real engines are not 100%. They're not as efficient as thermodynamics will allow them. So here's where I wanted to lead up to then. I showed you last time that when you compress just air or any gas, you do work on it. The energy goes into it. Where does the energy go? It goes into thermal energy. And that, depending on what you're compressing, it might actually catch fire. And what you're compressing in an ordinary internal combustion engine that burns gasoline, conventional engines that most people's cars have, during that compression stroke, it is possible for that compression to ignite the fuel and air without waiting for the spark plug. Oops. When that happens, the fuel and air burn, the burn doesn't occur in the location. in the path that was expected. It ignites at some uncontrolled spot within the fuel air mix, that cavity, and it's at the wrong time and to some extent at the wrong place. The ignition occurs, and the fact that it occurs too early, it occurs during the compression stroke, means that the compression has to continue further against very hot, high-pressure gas, and the engine hates this. This is not good. It's trying to squeeze stuff that doesn't want to be squeezed at all. So it's energy inefficient. It's jarring to the engine. You don't really want it to happen a lot. A little bit is no big problem. And in conventional cars, it happens most often when you're really asking a lot out of the engine, putting a lot of fuel and air into the cylinders. For example, driving up a hill. So you're driving up a steep hill. That's the most likely moment at which a car will begin to knock a little bit. Most of the time, the cars don't knock. And the reason they don't knock is because the gasoline has been tailored, in fact, chemically tailored, to be hard to light. And this is where octane number comes in. So when you buy the different grades of gasoline, it's the regular, middle grade, and premium, those three, the only significant thing you're buying that's different is the difficulty in igniting the fuel. The premium gasoline is simply harder to light on fire. It can tolerate higher temperature as a fuel and air mixture before it spontaneously ignites and knocks. The word knocking, pre-ignition, they're all the same thing, same concept. So there are cars that have high compression engines. That is, they squeeze the fuel and air mixture in more than normal. The normal compression of an engine is something like 8 to 1. It takes the volume before the compression stroke is 8 units, and after the compression stroke, it's down to 1 unit, something like that. There are engines that go 12 to 1, for example. And if they do that, the temperature they reach in that the fuel and air reaches during the peak of that compression can be higher, and the fuel may need to be special to avoid burning. But apart from these special engines, you don't need it. So again, public service announcement is those of you who are tempted, or have people are tempted to put in mid-grade or premium gasoline thinking you're babying your car. If it doesn't knock on regular, you're mostly babying the people who are selling you fuel. You're just transferring money to them. In fact, I think that the energy content of premium gasoline may actually be less than the energy content. The joules per liter may actually be less than in regular. So, because they have to go to stand on their head to make these high octane numbers. The classic way of increasing the octane, where octane is just simply a measure of how hard it is to light. The old way of making gasoline hard to light was a chemical known as tetraethyl lead. So maybe you don't even remember you haven't paid any attention to the idea of unleaded gasoline. Is that still familiar to you as anything? Unleaded gas? There was a huge transition about 40 years ago where they got rid of the tetraethyl lead, and there were cars on the road simultaneously that both required leaded gas and unleaded gas. Burning a lead compound is not great for the environment because it comes out the tailpipe as various lead compounds. Lead is not great for us, right? So they phased out tetraethyl lead. They had to bring in other substances that inhibited ignition. But tetraethyl lead turned out to be a great one, but it's environmentally nasty. Anyhow, if you ever noticed unleaded gasoline, it's a reference to this transition having to do with trying to keep the fuel from bursting into flames by accident, and yet not do that with something that's harmful to the environment, to us. All right? Everybody okay with the idea of gasoline and octane? Next time you're shopping for gas, that's what you're shopping for. Okay. Before I go any further, I'm going to go do a demonstration. One that I meant to do at the end of I was thinking of doing last time. Just to show you how much energy there is, because got to have a few explosions, how much energy there is in a fuel and air mixture. I will mix, well, not air and gasoline, but air and alcohol, methyl alcohol, because I don't know. I guess we could use gasoline, but methanol seems more scientific. Ooh, methyl alcohol, methanol. Okay, so I've got a fuel and air mixture. The methanol evaporates pretty easily, so it's spreading out of there. And I'm going to ignite it with that guy. Just instead of a normal spark plug, you got like spark plug on steroids here. That ought to light it, right? Okay. I'll undo that. Oh, come back. That instantly, that device was historically known as a Ford coil. Was the igniter back in the old Ford, like Model T Ford? They used Ford coils to do that. That was the type of spark they used. Okay, so this now, if I put it on gently, I'll put it on gently first because this will go up in the air more than it will do anything else. Ready? Get set. Oh, come on. Boring. Okay. But that's kind of, that is boring, right? So no sound. So this time I will shove it on tight. And gotta make sure it evaporates properly. All right. This time, put it on tight. Take that. Ready? Get set. Oh. Here you go. Try again. Ready? Well, that's good enough. Or maybe not. Maybe. Come on. You gotta have one burst. I gotta get air in it properly though. Got out with the bad air, in with the good. The size is it's fried. Ready, get set. Man. Teach me to try to do this demo. Ready? There. All right. It was worth it, wasn't it? All right. What was happening? I think the main issue is we were trying to get the methanol to evaporate properly. It was really having a tough time getting into the air. So I was trying to light basically air. Eventually, it was a real mixture, and then it lit properly. Is that what your question? Oh, why did it bang? Why? How is it related to the automobile? That is what happens at the beginning of the, in fact, more intense version, at the beginning of the power stroke. You're compressing a mixture of fuel and air, so the same kind of mixture in a cylinder has been squished to very high pressure and density, so it's really packed tightly. This was at atmospheric pressure to start with, and in the cylinder, it's at 20, 50 times atmospheric pressure, having been squeezed and heated. So the flame occurs very fast, very hot, and it's trapped in metal. You can see why the metal has to be pretty sturdy to put it so that it does work. It pushes a piston out rather than simply bursting through the sides of something. So this milk jug will no longer hold water, so to speak. So where's the burst? Oh, it went out through the handle, which is kind of cool. Unlike, an unlikely spot to blow, but that seam exploded. Other questions? So the point is that was just a little tiny bit of methanol and quite a bang. So this is what you can imagine when you get gallons of, that's a gallon of gasoline. So over the course of 20 miles, wherever your car gets, it's using that to propel a car. All right. Two last pieces to deal with. One is the diesel engine. I mentioned this a little last time, but I'll finish it out. A diesel engine doesn't add the fuel before it compresses the air. It compresses pure air. What are the disadvantages? Well, disadvantages is because then you're going to have to deal with the fuel later. But the advantage is you can compress the air as much as you like. It will not burst into flames. It's just air. It's already, just air. So a diesel engine can go to higher compression and therefore reach higher peak temperatures because it's just squeezing air. The consequence, though, is that it has to now inject the fuel at the end of the compression stroke and beginning of the power stroke. So it needs a specialized injector. It shoots the fuel in at fantastic pressure. So the pressures of the fuel injectors in a car are high, but in a diesel engine, they're like 30,000 pounds per square inch, 30,000 PSI. So just tremendous pressure, way beyond a power washer. And in much less than a thousandth of a second, they also have a valve that opens and closes in a tiny fraction of less than a thousandth of a second. So it opens and closes, it fires this pulse of fuel into the already compressed and therefore already very hot air. And the fuel bursts into flames just on exposure to this tremendously hot air. And so it burns and then does the power stroke much like in the gasoline-powered engine. The big advantage of a diesel engine is that you can the burning occurs at a higher temperature because you can squeeze the air harder. And therefore, it is more energy efficient. The hotter hot, it's able to extract more of the thermal energy as work than a gasoline engine. And this is why, if you've paid any attention to gasoline engines versus diesel engines are more energy efficient. Second piece of this is, with diesel fuel, you actually want it to burst into flames easily. So you don't want all the engineering that goes into gasoline that makes it hard to light. You want it easy to light. So diesel fuel is very simple. They're very simple hydrocarbons usually. You can almost use the hydrocarbons right out of the ground. And there have been people who made diesel engines run on almost anything. If it burns, you can use it. So this is why you get biodiesel and so on. You can't do biogas, not so much. It's much harder. Biodiesel, much easier, at least comparatively. So they're more energy efficient. They do have one big downside, and that is that the fuel doesn't always burn perfectly because you don't pre-vaporize it. It's going in there as little tiny droplets, and the droplets go through the burning process, burns most of the stuff, but it cooks some of the droplets into little crisps, into little pieces of carbon, and carbon and maybe a few other things in there, and makes tiny particulates. And the tiny particulates have been a reason why consumer ordinary diesel cars have had a complicated history in the United States. They're very common in Europe. Diesel cars dominate in Europe, and diesel fuel dominates in Europe. They're more energy efficient. It's easier to make diesel fuel, actually. It's odd that the diesel fuel is more expensive here in the United States. I don't understand that. That's some economic thing, because diesel fuel is easier to make. But in the United States, diesel engines have been iffy because you've all seen trucks. Trucks usually use diesel engines. And if they're not burning stuff properly, they're crisping the gas droplets and blowing them out as black smoke. So you've all seen the black smoke come roaring out of diesel engines. Nasty. People have figured out how to get most of the particulates out of the exhaust. It involves filtering. And that actually brings me to the last topic to talk about here in general. Why do cars have catalytic converters? Diesel cars actually have more complicated system than a catalytic converter because they actually have to get rid of the particulates. And so they have these filters that collect them, that collect the particulates and then subsequently burn the particulates. So there's a cycle within the filter. So if you buy a modern diesel car, it will have a high-tech filter in there to get rid of the particulates. But any car on the road today, hopefully in the future too, we'll see what happens with EPA and stuff, but having devices in your car that catch the unwanted consequences of burning fuel and processing has been pretty important for a long time. What the catalytic converter does is it takes things that came out of the engine. The engines are all now computerized, and they're monitoring. In principle, they're always monitoring to make sure that they get the right mixture of fuel and air. If you have too much fuel, not enough air, you get incomplete burning. You get carbon monoxide, for example, which is toxic, and you don't really want it around. If you have too much oxygen, not enough fuel, then you're likely to convert the oxygen into things other than carbon dioxide and water, like the nitrogen oxides, I suppose. So anyway, the catalytic converter uses the surfaces of tiny, they use noble metal surfaces, noble metals being platinum and rhodium primarily, I think. Very expensive metals. The reactions occur at the surfaces of those chemicals, and therefore you want to have as much of the metal involved in the surface as possible and as little inside the metal as possible. So they use tiny particles of these metals. So that almost all the atoms are on the outside. They suspend those particles in a sort of ceramic matrix, and then they let the molecules that come out of the engine that you don't want, carbon monoxide, fuel that simply didn't burn at all, the oxides of nitrogen, which aren't really are undesirable also. They're all of them, well, most of them toxic. Nitrous oxide is laughing gas. I guess people wouldn't mind too much if that's all that came out of the engine. But nitric and nitrogen dioxide, not so good. So these noble metals, they operate at higher temperatures. Like they're heated up by the exhaust gas itself. So once you've let the engine run for a minute or two, these particles in their ceramic holder are hot as the molecules the unwanted molecules pass across them. Those noble metals facilitate the breakdown of those molecules. They catalyze it. Catalysis is a phenomenon where certain molecules or surfaces or structures facilitate reactions without actually permanently changing themselves. So they sit there and keep on helping the reaction go by. And so the catalytic converters have dramatically dropped the garbage that comes out of the exhaust of cars. They've been around probably, really, they started appearing about the same time as the transition away from leaded gas. So this is in the early 80s. The reason they had to happen at the same time is because lead is toxic to these catalytic systems. It coats the little particles, so you get a lovely lead-coated particle of platinum or rhodium that does nothing. It's like you can take you take your lovely jewelry and coat it with lead. Wow, I've got a lead-coated gold ring. Isn't that cool? So, yeah. All right. So, catalytic converters, trying to reduce the nastiness of the exhaust coming out of engines. Any questions about cars in general? Main issues, heat engines, you're okay with heat engines? Hot to cold. The world's full of natural heat engines. The winds are natural heat engines, ocean currents. Okay. With that, then, I'm going to leave the world of thermal physics and thermodynamics, go to something completely different, the last of our topics, the last of our overall stories, resonance. And my first topic in that context is clocks. So, if you go out on a springboard, so you're going to go diving, and you stand on the springboard. This is I hope a familiar question, because I asked you back. You go out on the springboard and you bounce. You let it settle down, and a friend comes and joins you. It bends. It's basically the springboard's a spring. First word, spring, right? Anyway, you go out on the end of the springboard and you bounce up and down a little, without leaving the board. So you and the board are one object. If you leave the board, life gets complicated. But if you stay on the board, you bounce up and down. For one day when the boards aren't here. Well, broken springboard. It's a javelin. So you go out on the springboard and you bounce up and down. Boom, 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 boom. If you bounce a little farther up and down, so instead of bouncing a little, you bounce a lot, how will that affect the time it takes to complete one bounce? You can picture you're boing, 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 1, 2, 3, and you bounce a lot, a bigger bounce. 1, 2, 3. You don't leave the bot. How does it affect the time? So if you bounce farther, will the time it takes to complete one bounce increase, decrease, or stay the same? Okay? How many think that it'll increase if you bounce farther? How many think it'll decrease if you bounce farther? How about stay the same? Okay, the majority are going for increase. There's a split of about a quarter each maybe for decrease and stay the same. The answer, remarkably enough, is stay the same. Okay? And it's a little hard to show you with this guy. I'll try it. I don't actually have to put anything on the springboard because the springboard already has its own mass. So if I make it bounce a little bit, ding, 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 can I make it slower even than that? This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. About that pace. Now I'll go harder. 1, 2, 3, 4, 5, 6. It's about the same pace. In fact, it's exactly the same pace. So the weird observation is whether it bounces a little bit, whether you want it or without you, or bounces a lot with you or without you. It takes the same time to go through a bounce. Now, that seems troublesome because if it's got to move farther, that should take longer, right? It's going to go way up and down. That seems there's bigger motion, bigger extent of the motion. Shouldn't you have to pay for that? Well, if you bend it farther away from center, you've bent that spring more. And springs, as you recall, fight. They exert a restoring force that's proportional to how far you take them away from center in equilibrium. So, as you make a bigger bounce, the spring force, which is actually part of the motion, gets stronger. And it perfectly compensates for the bigger motion. So that's actually sort of the central issue of the story of clocks. Clocks keep time with the help of devices like this, like that springboard, that has a motion that it goes through cyclically and naturally, and the time it takes to complete each of the bounces doesn't depend on how big the bounce is. That turns out to be important to clocks because it's relatively difficult to control exactly how big the motion of some rhythmic device is. It's like controlling the loudness of think of some music. When you smack the tine of a xylophone, you had as a kid one of those Fisher-Price xylophones. If you tap it a little, you tap it a lot. How loud it is varies a lot, but the pitch is always the same. This is actually sort of getting ahead of ourselves. But But clocks have trouble controlling how big the motion is. And therefore, having a motion that's got a rhythm to it that doesn't depend on how strong that motion is really helpful. Okay, so about clocks in general, they divide time up into uniform intervals. Somewhere way back when people started being interested in dividing up the day. You had certain intervals that we knew about. We knew a day is a natural thing. You watch that happen. The year is a natural thing. You watch that happen. The moon, the lunar month is a natural thing. But if you want to divide up a day into pieces, well, it's hard to judge. And somewhere along the line, the marketers for breakfast and lunch food probably wanted to make sure that you knew exactly when it was lunchtime so that you would feel hungry. Anyway. So they invented clocks to divide the world up, divide time up into uniform intervals. And the easiest, most successful type of clock is one that naturally goes through a rhythm, that ticks off time in intervals without any human intervention and without a lot of fuss. And so people started inventing clocks that are based about these rhythmic devices, like springboards for one, but pendulums, more importantly, devices like this. This is just a gigantic pendulum. It goes through rhythmic motion too, and that rhythmic motion is remarkably insensitive to how big the motion is. This is a little motion, but I can do a big motion, and the rhythm's the same. We'll come back to that guy. In the meantime, you're getting sleepy. All right. So why don't we use hourglasses? Well, hourglasses are fun for measuring a single interval, and they're pretty decent at doing that. But if you have to keep on flipping the thing over, it takes too much intervention. So we go on to things like pendulum clocks, which is the classic. My grandfather clock runs off the pendulum clock. A lot of wall clocks of 200 years ago were pendulum-based too. If you wanted a clock that was portable, pendulum doesn't cut it anymore. You don't want to be walking around with your wrist like this. So you have to go over to something that manages to tick off a rhythm without involving gravity. This involves gravity. And so what are known as torsion balances became popular. And lastly, the torsion balance, if you've seen a classic pocket watch, for example, you open it, it's got a little ring that goes back and forth, tick, 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 tick in it. And we'll look at those later on. But that's a portable device. It is relatively insensitive, in fact, remarkably insensitive to gravity. It allows you to carry your timekeeper with you. And in recent years, I mean, before the cell phone era, when everybody's clock is really not a clock at all, but rather a digital display based on somebody else's clock. I mean, the clock is no longer, to an extent, you don't have the clock in your hand anymore. The clock is located elsewhere. The classic clock that you would have yourself is one like this. The quartz wristwatch. A few of you still have quartz wristwatches. Those, interestingly enough, still have a rhythmic element in them. They're still going through the motion. The rhythmic element is a little teeny tuning fork. The tuning fork, a musical tuning fork looks like this, and you smack it, and it vibrates. It's instantly a lot louder if you give it a surface to project sound with. Right, can you find a surface? Can you hear the difference? It's not very good. I'm not. Yeah, we'll work on that when I get around to musical instruments. Projecting sound is difficult with thin things. They need surface things. Anyhow, it turns out there's a tiny tuning fork in any quartz watch or quartz clock. You open it up, you'll find it's a little teeny can about the size of bigger than a grain of rice, but not much. And it's got a teeny, tiny tuning fork inside. Okay, so these are all devices that keep nice time. And repetitive motions. Natural systems that naturally go through repetitive motions can consist of basically any device, any system that has a stable equilibrium. And if you think about, remember, stable equilibria are ones in which you disturb the object away from that equilibrium, it experiences restoring forces, forces that push it back toward that equilibrium, try to make it accelerate that way. And if you look at the motion of an object that has a stable equilibrium, just any one of them, we've done this before, things the system that does this, that has a stable equilibrium, it will sit forever at that stable equilibrium if it was at rest when the story started. But if it was moving when the story started, it will accelerate back towards the stable equilibrium, and when it gets there, it will still be moving. In fact, it will be moving, that's the moment at which it's traveling fastest. Remember this idea? If you're bouncing up and down on Ruffner Bridge, when are you moving the fastest? Well, it's when you're moving right through equilibrium. When are you accelerating the strongest? When you're the farthest from equilibrium. I hope this is familiar. And so things go, a system that has a stable equilibrium will keep going back and forth about that equilibrium. Every time it gets the equilibrium, it'll coast through. And then it'll turn around and come back and coast through. And then it'll turn around and come back, coast through, back and forth. And it has these characteristics that it hits maximum speed at equilibrium, and it hits maximum acceleration at the ends of its motion. All right? So those are all systems that will oscillate. Not all systems, however, are good for clocks. An oscillating system that is not good for clocks, and I didn't bring in a ball. But if I drop a ball or something like a ball, let's do it. Yeah, that'll do it. This is a stable equilibrium, that. And I can make it oscillate around stable equilibrium. Boom, 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 boom. It goes bum, 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 right? You know the bounce of a ball. It's not rhythmic. It gets faster as the bounce gets weaker. So the bigger the motion, the slower it is. Not all systems that have a stable equilibrium keep good time. Tick off the time uniformly, sort of independent of the situation, in particular how big the bounce is. There are special systems that have stable equilibria and that go through the motion rhythmically in a way that does not depend on how big the motion is. And those are known generically as harmonic oscillators. And the real definition of a harmonic oscillator is the following. It's a system that has a stable equilibrium, and the restoring effect, a force, for example, that acts on it, on the thing, the part that moves, is proportional to how far the thing is from equilibrium. In other words, the restoring force is spring-like. Remember springs? Way back in the Dark Ages, we talked about springs, and the observation that springs obey Hooke's law. Hooke's law says that a spring exerts a restoring force that's proportional to its displacement from equilibrium. Double it, pull it 1 unit away, you get 1 unit of force back. Pull it 2 units away, you get 2 units of force back. 3, so on. Remember, that's Hooke's law. Hooke's law and harmonic oscillators are like this. They're best buddies. So a harmonic oscillator is a system that has a stable equilibrium and a Hooke's law-like restoring force. Turns out a lot of things have Hooke's law type of restoring force. Anything that involves a spring does this. Things that don't have obvious springs also have this. This pendulum, interestingly enough, has a restoring force that follows pretty much a Hooke's law. That is, when it's dead on center here, that's equilibrium. If I pull it away from equilibrium, it experiences a force that pushes back towards equilibrium. To remind you way back when, one way of knowing that is because the total potential energy of this thing increases as I take it away from equilibrium. Therefore, it develops a force back. Things accelerate in the direction that reduces their total potential energy as quickly as possible. Well, the farther I take it away from equilibrium, the stronger the restoring force gets. Why? Because you can think of it as kind of riding, at any given moment, it's sort of like it's riding a ramp. And things, if you remember ramps, an object experiences a downhill ramp force. And the force is proportional to how steep the ramp is. Well, down here, near equilibrium, the ramp's not very steep. But out here, the ramp's steeper, and it increases in steepness just right. So the restoring force, the force back towards center, If I go 1 unit over here, we get 1 unit of restoring force. If I go 2 units over here, I got 2 units of restoring force. 3 units of restoring force. It works, and it's symmetric around the equilibrium. It all works out. So a pendulum has a spring-like restoring force, and it qualifies as being a harmonic oscillator. So that's a harmonic oscillator. This is a spring. I mean, it's a weird shape. You're used to coil springs, but this is still a spring, and that has the right restoring force. This is the classic harmonic oscillator. It's a mass, an inertial thing on the end of a spring, literally a spring. And this guy, if I bounce it a little, tick, 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 or I bounce it a lot, tick, 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 tick. It satisfies the requirements of a harmonic oscillator. Stable equilibrium, and restoring force that that's proportional to displacement. What you get when you have a harmonic oscillator, so I've defined a harmonic oscillator. You get a benefit when you have a harmonic oscillator. And the benefit is that the period of the oscillation, which is the time it takes to go through one cycle, that's period. It's up here. The definition of period is right here. Interval between 2 repetitive motion cycles. The period of a harmonic oscillator does not depend on the amplitude of the motion. There's amplitude right here. The peak distance away from the motion center. So if you have a harmonic oscillator, you get this crazy great benefit, which is the time it takes for the motion to go through its cycle is independent of how big the cycle is. You can see it pretty well with that bouncing mass there. You can do it here. One thing about having my own is I can time. So here's a little motion, and I'll do 5 cycles. 0, that's your starter. 1, 2, 3, 4, the board. 23.4 seconds. Now if I do a bigger one, we'll hit things. Zero. 1, 2, 3, 4, 5. 23.1 seconds. No, so within my ability to control it, I was off by 3/10 of a second. It's the same period. And this is why pendulums are good as timekeepers and why they're so common in clocks. As long as that pendulum is swinging, whether it's swinging a little or a lot, it's ticking off time in very uniform intervals that do not depend on the size of that swing. They depend on other things. What we'll see next time is the pendulum has a restoring, well, the pendulum's period depends on 2 things. One is the length of the pendulum. The longer the pendulum is, the slower it goes. Here's a short pendulum. It ticks faster. Medium pendulum, somewhat slower, slower still, and finally very slow over there. So the length of the pendulum matters. The other thing about that determines the pendulum's period is the strength of gravity. And that's an unusual thing, but interesting. It means that pendulum clocks tick off time beautifully uniformly, but you do have to adjust for the local strength of gravity, which varies from place to place. I've talked about that one before, too. So when you install a grandfather clock in a certain location, you have to adjust its length very carefully to get it to tick time properly. So, for example, the one up in Monticello has been there for 200 years. It's a pendulum clock. Surely they adjusted way back when, adjusted it to swing, to tick time off just right, given the local gravity up there on the, I forget what the name of the mountain is. It's not Carter's Mountain. What mountain is it? Anyway, it's probably Monticello. Anyhow, so pendulum clocks. We'll next time, Monday, I'll look at pendulum clocks. I'll look at more portable clocks and see See how far we get.